All right, so Mike, it's my pleasure, by the way, to welcome Giovanni Motta, who has been my collaborator from Colombia. We've been working for a year or more now, right?
Yes.
With several of his students working on first on what you're going to hear about, which is modeling stellar light curves from tests, and also on images. So who do imaging analysis will probably also find it interesting. But that's another talk. But for now, Giovanni is going to be talking about light curves. And I should also mention that this is a preview of his talk at the JSM. He's giving a talk on a similar theme there. So take it away, Giovanni.
Thank you very much, Vinay.
Oh, one other thing, sorry, just to mention to people who may be unfamiliar with the way this CHASC thing works, feel free to interrupt at any time. We treat these talks more as discussions than lectures. So go ahead, John.
So, but in principle, how much time do I have?
In principle, you have more than an hour.
More than a, so it's a lower bound, not an
Yes.
upper bound. Okay, so yeah, I'm very happy to be here again. I've been here 4 years ago. Yeah, it was
Just the week before we closed down for the pandemic.
Yes. Exactly. Yeah, so it's nice, and yeah, thank you for inviting me. So this is a joint work with Johnny Wang, who is a PhD student at Texas A&M, and Vinay, of course, who is here in the room from CFA. Harvard and Smithsonian. And yeah, so the goal of this project is to detect stellar flares. And so the title is really concise. It really mentions only, say, the stochastic part of the problem, yeah. But it is also actually the main novelty of our approach. We use an approach which is used in finance. So we first, when we sent data, and I was simply differentiating the data, I realized the data looked really like financial time series. Yeah. But the goal is really to detect so the flares. And as I'm going to show you, another important component of the, say, an important, say, task here is to remove the non-stochastic part, the deterministic part, because so the deterministic part for this kind of time series can be pretty complex. So I like to show you what we have in mind. So these are the light curves we study. Yeah, so for this talk, I picked these 4 stars. Actually, these are 2 stars, right? Because
no, it's the same star. There was a gap in
the first. So actually, there are 2 stars here.
No,
what the first, the second, and the third is 1 star.
Oh, that's right. Sorry.
Yes. So this panel, and this panel is 1 star. So, and the very last one, bottom right, is another star. And as Vinay was mentioning, these are different chunks of the same stars, the same star. And so the reason why I really picked different chunks of the same stars is really to highlight how even within the same star, you can observe very different behavior in terms of, say, the deterministic component and the random component. Yeah, so like so you can notice, for example, here, of course, these are periodic time series. Okay.
Now we can still see. It's okay.
So these are periodic time series, yeah. But immediately you can see that, for example, the amplitude of the time series changes over time, and even also the frequency change over time a bit, and eventually even the phase. So this is the first task. So we need to take care of, and then once we remove the deterministic trend, we realize that so the stochastic part was characterized by these, say, random or non-deterministic, say, explosions or, say, bumps that can be captured by some financial time series models. Okay, so a little bit about this. So here I'm gonna mention what I've learned from Vinay. Yeah. So flares are impulsive events that release large bursts of energy over short time scales. And they have some important effects on the spectacular aurora, satellite communications, and so on. And so here, so what we need to mention is that so they occur when magnetic energy stored is released. And so they occur mostly where strong magnetic fields are present, for example, around sunspots. And these areas are called active regions. However, flare onset is poorly understood. That's where we are working. And so one of our major results is that the residual light curve, so the light curve you obtain after removing the deterministic trend, can be nicely modeled by a Garch process. So of course, I'm going to clarify what the Garch process is, main properties, and why we are using these type of time series processes for our problem. Okay. Okay, one little bit more about the motivation. The studying stars is an excellent way to improve our understanding of the sun. Why is that? Because they allow us to look at how the sun would behave if it had a different mass, age, or composition. Yeah. And so our contribution here is to develop a method that we apply to test light curves in order to gain insights into flare distributions, cadence, and onset. Okay, so these are the time series, the light curves we're studying, the transiting exoplanet survey satellite. And so as I mentioned already, the Garch process has been used in econometrics. Yeah, and in particular, we want to study the so-called volatility index, which is volatility means basically time varying standard deviation of the time series, more precisely the conditional standard deviation, given past information. Okay, what is the goal of this project? We want to define the model. We want to introduce a good model for this kind of data. And we want to eventually in the future explore differences with spectral type, with stellar age, and activity levels. Okay, so this was a little bit about introduction, motivation, introducing what flares are. And so our new approach is a semi-parametric approach in the sense that it combines a first step, which involves a non-parametric, or more precisely, by non-parametric, I mean local estimation of these time varying variants. And in the second step, we use a parametric approach to test whether at a certain time point we have a flare or not. Okay, so of course, I want to detail both parts of our approach that translates into an algorithm. And so at the end of my presentation, I want to show you that flares can be really detected as significantly large deviations from the baseline. By baseline, I mean the time varying periodic deterministic component. And as I said, we apply this methodology to two stars that we observe in three different chunks. And so, and the first one is a star we will be observed in three different chunks, and the second star, we focus on one specific chunk. Someone is chatting. Perhaps you can take it.
Oh, yeah. So there's a question from Bernard. Go ahead, Bernard. I mean, but do you want to ask the question, Bernard, or do you?
Oh, sorry, I put it in the chat. Sorry, this was just what type of light are you analyzing those light curves? I know when I talk to we analyze X-ray light curves, but are those visible lights?
Yes, actually, they're from CHASC light curves. They are what is specs really? It is it is reddish bands, let's put it that, reddish like this.
Okay, thanks.
Okay, so in my talk is really split into two parts. Yeah, so the first part is so removing the deterministic component. Yes, and the second part, testing. And as you're gonna see, these two parts are, say, interacting with each other. So before going into details, I want to give you, say, since day one, a snapshot or a summary of what's gonna happen now. So I have the original time series, the blue light curve, the red here, the red curve is our fit. Yeah, it's the fits that you obtain by using some time varying harmonics. Yeah, and once you obtain the residuals that are plotted in the second here plot, we apply we follow a procedure based on hypothesis testing, where we divide the residuals by a robust localized estimator of the standard deviation. Yes, and then once we are able to obtain the residuals, we can fit the parametric model, the conditional volatility, and those red spots are what we call flares. And if you go back to the very first figure, you notice that once you plot them back on the very original scale, you notice that those dots correspond to what Vinay was pointing us out as being flares. Okay, so this is really like a very short summary of my talk. Okay, we introduced the concept of flares. So I want to talk about our statistical model. Yeah, as I already mentioned, it's composed by two parts. I have the deterministic trend and the stochastic errors. And in order to properly and precisely detect the flares, we need to take care of the trend of the detrending part. And why do I say we need to take care of that? Because those trends are not regular in terms of amplitude or phase or frequency. Okay, the second part, so the stochastic error is what we model using the conditional heteroscedastic volatility. And another question?
No. I was just answering.
Okay, and then I will introduce our approach, which is a combination of two different tests, non-parametric and parametric. And then I want to show you how the method works with those stars I've been introducing at the beginning. Okay, maybe I can put this down. Okay, yeah. So our model really looks like that. I have a non-random trend plus a stochastic error. Yeah, and so the function mu is deterministic, periodic, and allows for time variation in its coefficients. And the errors follow a Garch model. Yeah, a Garch model is capturing the conditional variance of a time series, conditional given the past, in this way. And so the conditional variance of a Garch model is a weighted average of past or lagged square values of the process and past or lagged square values of the volatility itself. And so from this last line, equation 3, it is obvious that the volatility is stochastic. Yeah. It is not deterministic. Yeah. There are other approaches that we've been following in the past, like smoothly time varying variance or mean or parameters, deterministic ones. But here we want to, that's why we use the Garch. Basically, we want to model and explain the stochasticness or the randomness in which the volatility behaves.
Oh, don't worry about it.
Okay.
I'll monitor the chat.
Okay. Yeah.
Actually, sorry, can you go back?
Yeah.
So I was trying to understand what the P and the Q actually mean. So if you have highly spiky light curves, that means that P is small and Q could be anything, right?
It depends also on the sign of the coefficients. So to answer your question, I was expecting such a question, and actually, if you square a gauge process, you obtain an ARMA PQ. It's not difficult to prove that if you have a gauge process X, you square it, yeah, the squared time series follows an ARMA PQ process. So now, of course, a lot depends also on the sign of the coefficients, yeah, but typically P and Q are small. In practice, are small, like of the order 1 or 2. Yeah, so, and if you think that, so the square values of the axis are ARMA, then it's obvious, I mean, it's easy to see that basically the second part, the betas play the same role as basically the AR part of your process, and the alpha, the MA part of the process. Okay, so
Shelby has raised his hand. Shelby.
I just want to ask a question about, I know the Garch model is very popular in economics, in finance, but my understanding is I always consider Garch model is a kind of a desperate model, meaning just, because it's all empirical phenomena. There's not much real theory behind it other than or intuitive notion, something should be varied, something should catch these variations. So since you're applying to in this context, is there any physics series to support this kind of model, saying there is some real scientific understanding that this kind of model will work other than a kind of empirical model?
Yeah, actually, so let me touch upon, let me follow up with the first part of your question, because for the second part, I mean, the answer is I don't know, and I will pass it to Vinay, who is here in the room. But actually, you're right. So a gauge process is a white noise, right? A gauge process satisfies the assumptions, the hypothesis, the assumptions of a white noise. Gauge or large processes become interesting when you condition. And why is that? Because you want to capture this local clustering of volatility. So you have, so high volatility is likely to be followed by high volatility, and low volatility is likely to be followed by low volatility. So this is to follow up with your, so about your comment, but I do not know whether gauge processes, strictly speaking, do possess, do explain the physics behind the light curves we're studying. So maybe Vinay.
No, that is what I would like to know too. I mean, the fact that Gauge seems to do a good job of modeling these things. I mean, this looks like Gauge, as opposed to ARMA or Karma or OU or something like that. So, I would like to know what that means. I don't honestly know. So,
so this is actually a figure that the very first thing I've done when Vinay sent me the data, I differentiated the time series, and I noticed that so the residuals of the light curve Vinay sent me, the structure of the residuals looked very similar to the structure of the returns of the Dow Jones index in terms of volatility. So yeah, so your question is really interesting. Of course, that would be a striking result, understanding so the physics, whether the physics can be modeled this way. But if you from an empirical point of view, from an observational point of view, so you see you have the return of the Dow Jones have this feature. So this high volatility is likely to be followed by high volatility, then low volatility, and high volatility again. And this seems to be similar to what happens with the stars. Now, if you look at the figure here with the stars, I'm looking at the residual of the light curve. Yeah, there is still some periodicity which was left. Yeah, in the star, and that's why I simply differentiated the series, but I didn't take care of the periodicity. If you look at the second line, notice strong similarity between the conditional volatility of the light curve and that for the Dow Jones index. So this was really like, of course, it doesn't answer your question, yeah, but actually, after working for a while on this problem, we noticed that some other authors were using the GARCH, right, to model the residuals, but it was different types of light curves, those X-rays.
Yeah.
And yeah, so apparently, so this class of models has already been used by other astronomers.
Glenn has a question.
Oh, it was kind of a follow-up to your question, Giovanni, about, can this conditional volatility help model the physical nature of the stellar flares? And so I guess one thing you could look at is the sort of the decay of the stellar flares. Like once you've identified them, does this GARCH model help you identify the duration of the flare? Because that's really what's of interest, I think, to astronomers.
If I may comment on that. So yes, the problem here is that these are test light curves, so you know what that means, right? I mean, they're going to be short, so it's very difficult to measure a true decay time scale. But generally speaking, yes, I believe that can be that. When we fit a GARCH PQ, the longer the duration, the longer the decay time scale, the larger the PV, right? So we should expect to see small p compared to, I don't know, sometime maybe in X-rays where p would be very large.
Right.
I know that's at least part of the interpretation. I don't know what Q means.
Right.
Can I ask you a question?
Let me jump in and say, oh, sorry, go ahead.
Okay.
Go ahead, finish.
Are taking into account any actual instrumental noise from TESS itself? Because I think TESS famously has correlated noise.
Yeah, we're using the decorrelated.
Okay.
So yeah, it's the best that TESS can give us, but we're not doing anything fancy. Sorry, go ahead, Sean.
Just a little bit background here. I think the reason I said what I said about these models is basically the fundamental thing we want to do is say at any time there's a distribution, it depends on the previous distribution, right? That's the relationship we're trying to capture. Now, in the finance literature or in all these volatilities, because what they really care is the variance, because they use these variance to actually price, options, to do all things. So they take the variance as a very fundamental quantity. Now, so what they do is they say, okay, the traditional time series is say it's like the average, the current average depends on previous average, right? Then someone realizes, okay, now that's not enough, because how about the current volatility depends on the previous volatility as well as depends on the previous average, right? So that's they come up with what I call desperate model, because you basically put everything there, right? then trying to fit it. Now, for their purpose, it's entirely fine, because they price all this stuff according to these. So they actually it's essentially like they define the reality by the model itself, right? Because they do those things. So the question here is the interest to me. I think for us to think about fundamentally, like in terms of physics, like at any time the distribution, what the quantity will depends on. Because currently, with basically GARCH still say all what's important is the mean and the variance, except that we have a more complicated variance, depends on the previous ones, right? And for lots of those things, to me, is like some skewness probably is quite important. And so the question is like really, I want to push we to think about what is the relationship between one versus the previous ones. Okay, great. You have the ketosis there. So yeah.
Yes. So you can. It's not difficult to prove that the XT has heavier tails than the epsilon t, in the sense that the kurtosis is larger than that of epsilon t. And actually, I mean, this is not new. Yeah, there are some say justification to fit heavy tails T distributions, rather than the Gaussian distribution to the errors themselves. Yeah, so yeah, but the answer, I think partial answer to your question is here. Of course, this is just the kurtosis, not entire distribution. Yeah, but this is exactly what we've done today with in order to test whether the conditional volatility is, say, larger than a certain significant quantile. So with Johnny, yeah, we found out that, so when we look at the conditional variances, actually they follow a generalized chi-square distribution. And we use that piece of information to test using using this p-value, to test whether the conditional variance is exceeding say the observed sigma squared t. So perhaps this answers better your question.
Well, I guess thank you. I know this model obviously is rich enough because you have all these parameters. You can capture those things. I was really pushing us to think about, maybe even they can think about some rationale saying all we care about is the first two moments, and this relationship is rich enough to
That's
capture
correct.
those things. Then
That's correct, and I think I mentioned that. So this is different than, for example, what the class of locally stationary processes does. In that case, you have smoothly variant parameters, and there is a dichotomy between the processing domain and frequency domain. Yeah, so that's no parametric, but this is fully parametric. So you have a few parameters governing the whole process, as you said. Yeah. So, yeah, so the first part is important because once so if your deterministic component is very complex and you do not adaptively remove say that deterministic component by allowing for some time varying amplitude and frequency, then the flares are not detected correctly. Okay, so we use a model which is very general. Actually, it's a model that looks like a standard harmonic model, but with coefficients, that are weighting the cosinus and the sinus waves are changing over time. Eventually, you can also fit these kind of models to unequally spaced time series. Yeah, and so we use the same approach we have been used for another paper for this part using penalized B-splines. And what I want to for today's talk mention that this is actually this kind of modulating model includes as a special case the so-called amplitude modulation and angle modulation. And I want to present these few slides to give you a more, say, better idea, more clear idea about what we have in mind. So amplitude modulation is basically an amplitude which has been corrupt, or it has been, to which you have been injecting a so-called modulation signal. That is such that the amplitude is going to be changing over time. Yeah, so you have your carrier wave, that we call CT, and then the modulation signal is a waveform, that you think of being transmitted. And as a result, you obtain the so-called modulated signal that contain both parts. So amplitude modulated. Yeah, so the original part, the carrier, plus this part that depends on the modulated signal. This is an example, just a specific example. I have a carrier wave of this form. And then it's the phase, this is the fundamental frequency. And then I have a modulation signal of this form. Of course, it's a special case. Yeah, and you obtain this kind of modulated signal that is convenient in the sense that it can be written in this way, where you can distinguish between the phase. So the phase that is coming from the carrier and the original carrier, and the phase coming from the modulating signal. And then for another more complicated example is an example where you have really a time varying output here, and which is weighting an average wave. And as a result, you have kind of more complicated signal. And the goal, I mean, I want then later on to give you a visual idea of what these kind of signals are able to capture. And the third example is an example of frequency modulation. Okay, so it's not, so you're going to observe changes also in the period of your harmonics, which is exactly what we observe using when we studied these light curves. And so you can think of these as being the modulating signal, and the frequency modulated signal looks like that. And so this picture gives you an idea of what we have in mind. So amplitude modulation, so you see I have the carrier wave that has this form. Okay, so basically it's apart from a constant, which is this value here, I have the wave in green. Yeah. And so the original carrier is the curve in black, which is just 10 times the curve in green. And then I inject into that signal, the modulating signal, so in blue. Yeah, so here I have the mathematical, say, result, and this is how it looks like. So you have variations in the amplitude, and you can see they're not necessarily even regular to capture. The second is also a change basically in the phase. So this is the original carrier in green multiplied by, say, the scale parameter, the modulated signal, and the modulated signal looks like that. Okay, and the last one is changing the frequency modulation. Yeah, and so you have original carrier as before, the modulated signal, and as you can see here, the signal looks even more complex. So the reason why we are really interested in these kind of so the last line here of this figure is that they really seem to mimic the deterministic component we observe in the light curves we downloaded from the TESS database. Maybe I can go back quickly to say relate to what we've seen in the very beginning. If you look, for example, at this part, which is the star I'm going to present in order to show how our algorithm works more in details. Yeah, of course, you have changes in the amplitudes, yeah, but you also have changes in the frequencies. Okay, so this was a star that was not easy to say model from the point of view of, say, the deterministic component. So there's questions about this figure or modulation. I think there are two chats.
Yeah, what?
Chats.
No. There are
Okay.
chats going on
Okay.
parallel.
Okay.
It's okay. There are no questions asked.
Yeah. So yeah. So that was for the deterministic part. How about the stochastic error? Yeah. So I start with the arch process. Yeah. Yeah. So an arch process takes this form. Yeah. Where so d sigma square t, which appears here as being the conditional volatility, is what you find when you condition the expectation of the square values of x given the past. It's not difficult to prove recursively that this technical equation is the conditional expectation of the square x given the past. The series is zero mean, yeah, and the unconditional process is uncorrelated. Yeah, that's why, as I said, a gauge is a white noise. So at the level of the process, unless you condition or you square, you do not observe any special feature in terms of autocorrelation or in terms of heteroscedasticity. It's only when you condition that you find out the structure. Yeah, it is.
That's zero when there is no signal, right? I mean, is that the idea?
You mean the first line?
No,
The second line?
yeah,
I mean, no, simply uncorrelated.
in all cases,
Yeah,
even when
the
there is-
unconditional covariant, autocovariance function is zero. At all lags except zero, of course, which is the variance. Yeah, so it lags zero. So when S and T are the same, then you get this. Yes, which is the unconditional variance of the time series, which also explains why you need definition at the sum of the
right,
AI.
so that is like the case when there are no flares. Because if there are,
Actually, this is always the case. Without flares.
without even
Yes.
even with the flares.
Yes, because this is the unconditional variance. It's not the conditional variance.
But for a null distribution, right? For the null case.
Yeah, but under the null hypothesis, yes, you have the unconditional and the conditional are the same.
Oh, sorry.
Yeah.
Okay. Yeah,
But here, what you're saying, you say the conditional distribution does possess a structure, but the unconditional does not show up that structure, but the structure is there. Okay, and yeah, and so why is this model so popular? Because it captures a few features actually. I want to show that here. Yeah. So why these models are so popular? Because they capture the so-called stylized backs of financial time series, which are heavy-tailed time series, uncorrelated. So this is actually what you were pointing out. So the autocorrelation function, the estimated one actually, here I should put a hat here. Rho hat is very close to zero for all x. And but actually, when you look at the autocorrelation function of the absolute value or the squared, they have slowly decaying behavior, similar to ARMA. Actually, as I said, a squared gauge is an ARMA. Yeah, and another important property is about the volatility. They are stochastic and persistent, in the sense that large fluctuations or even small fluctuations in the data tend to be followed by fluctuations of comparable magnitude. Yeah. And this is exactly what the sequence of conditional variances is able to capture. Actually, I do have a few examples. So these are the returns for IBM. Yeah, it's very long time series. And here, so I'm splitting the series into two parts, just to make sure that the fact that you have a long time series is not necessarily implying that the variance is changing over time. And here I'm computing ACF for both time series. Yeah, not significant, right? That's why, so the gauge process, Arch and Gauge really satisfy the assumptions of white noise processes. But when you take, so the squares of both first and second half, you obtain so sample autocorrelation functions that look like the ones of ARMA processes. I think this is another time series I can show again from real data. This one is an interesting one. Yeah, so this is Dow Jones Industrial Index. Yeah, so this is so you have here sustained periods of both high volatility and low volatility. Yeah? So this was October 97, this was August 98. Yeah, so the volatility, so high volatility, it tends to be, periods of high volatility tend to occur, in a certain clustered way. That's also why these models are said to capture clustered volatility. Yeah, and then low volatility, and then again high volatility, yeah, for a while, and then low volatility again. Yeah. So this really explains the idea of conditioning with respect to past values. Actually, yeah,
Just some comment. Yeah, okay. So if you conditional past value, I mean, this effectively means it's a causal process, right?
correct.
I mean, this kind of answers the question, for example, like what's the physics? I mean, there's a bit of physics, or I mean, just the assumption that the process is causal, right? So the current volatility only depends on the past value.
Right, but
Right? You cannot look into the future.
but it could be an R method, right? So anything that's conditional would work. So why this particular form? I mean, so for example, if you have this xt being sigma t times epsilon t, right? Then why that?
Actually, here is an important point, because actually, you can prove that so that the Garch or arch is a causal, admits a causal stationary solution. Now, I don't know how that relates to the physics of the line curve, but under this assumption, so that the sum of the AI is smaller than 1, that is a causal solution.
Maybe you got a problem, right?
Yeah.
Is it a unique
Yeah.
causal stationary solution?
Yeah.
Okay, that might be.
Sorry, so when you say causal stationary solution, does that mean that like each one is being affected by the ones before it in exactly the
That
same
you
way?
can write the process
Yeah.
as
Yeah.
function of only past values
Yeah,
rather than present or future values. That's causality. And that happens if, in this case, the sum of the AI is smaller than 1. For an AR1 process, which is the simplest possible you can think of, so the coefficient in absolute value is smaller than 1. Yeah, and stationary basically means that the moments of the time series are time invariant. They're not necessarily, strictly speaking, they're not the same. You know? That's why it's stationary and causal. Yeah. I think you have a point here. Perhaps we should think about this more.
That's a good, yeah.
For justifying the paper, presenting the.
Yeah.
Okay. Actually, I just need to back here. Okay. Okay, so now we know that there are 2 parts. Yeah, in the first, we first remove the deterministic trend, which is characterized by time varying amplitudes and time varying, say, phases or frequencies. Yeah, and in the second step, yeah, we want to detect the flares. So this is the first step, and the first step is the combination of, say, the trending and at the same time removing layers. So in the first step of the algorithm, we iteratively fit the trend. So we detect those points that we consider as flares, and then we do refit the trend again, yeah, to the deep flare time series in order to make sure that the flare does not create some artificial bumps, yes, that can be then basically avoid us to capture flares. So we say, okay, under the null hypothesis, I have a white noise, the conditional distribution is a white noise. And under the alternative hypothesis, I have indeed the Garch process. Yeah. And so what is important here, to say estimate is this conditional volatility. And for that, we use a robust time-varying estimator. And the main idea is to notice that this ratio also follows an F distribution with 1 and n-1 degrees of freedom. And once you take the square root of that, using that when n is large, the F does not depend anymore on the sample size. So if you like, you can look at this as a uniform quantile. Then you end up with the quantiles of the standard half normal distribution. Yeah, so we came up with this rejection region, which is pretty intuitive to understand. So you fit your trend, you remove the trend from the data, yes, and you look at deviations that are in absolute value larger than ST times the quantile. Yeah, so we reject the null if the p-value is smaller than alpha. And in the algorithm that I still have to present, actually, we also provide an adaptive method to estimate, to fix alpha, yeah, a good alpha, yeah, a good significance level. So we start with an upper bound, and then we select among all the values of the above probability, the ones that are the ones that are smaller than this alpha max, the largest among those ones. Okay, so the largest one among the alphas that are smaller than alpha max. Okay, and I emphasize this last point, yeah. So the presence of the flares really makes the estimated fit biased, yeah. So at any time in the first step of our algorithm, we do detect the flare, we delete that observation from the time series.
So one question, what do you mean by detecting a flare?
Well, that's actually a question that I asked really I cannot define it.
Well, no. In this case, it is all that means is that it's a sigma clipping process. So if it's more than some
Okay,
signals, then,
all right. So, but it could be just large fluctuation, not necessarily a flare.
yeah.
It's one point.
So this is only being done for the first part, where you calculate the baseline mu, which, the harmonic mu, right? So
Maybe I can answer this question with a figure. Can be, so I have this. Yeah, so for example, I have this data. Yeah. And okay, I can think, even if I'm not an astronomer, that this is a flare, right? And this is a flare. And I don't know, maybe this is a flare, right?
Yeah.
By eye, right? Yeah, but the idea is that, so this is what we call best harmonic fit, in the sense that it is the result of an iterative process where you fit the harmonic trend, and when after fitting the trend, you get your residuals. And in this step, you apply the test locally in time to detect the flares, and you delete those observations, and you redo, say you repeat the estimation of the trend. Okay, but still I didn't answer your question, but the answer to your question comes in the second part of the algorithm, where so we get back to the original time series, we remove the very last, so the best version of the trend, we get the residuals, and here I fit the Garch model, and and I use the parametric structure to test whether I'm exceeding or not the threshold.
And threshold is set by.
The threshold is the threshold is given by a quantile obtained by noticing that when you look at the sequence of conditional volatilities, you obtain a generalized chi-square distribution. So you say if this p-value is smaller than your alpha, then you reject the null that there is no flare.
where do the W's come from for the generalized chi-square?
Weights.
Yeah, weights of.
So a generalized chi-square distribution is a weighted average of some non-central chi-square random variable plus a linear trend. Yeah, and so this W is weight. And why WT? Because we do the job locally for the Garch.
Oh, W is fit to the, okay.
Yeah. Okay. Okay, I think at this point I have enough ingredient to present the algorithm, and maybe so if there are questions about, say, steps in the algorithm, any steps in the algorithm, maybe I can say unpack what's in there. But this
Oh,
is,
Gwen has a question.
Yeah.
Gwen, don't worry about raising your hand, just
Oh,
jump in.
okay, sorry.
jump in.
So just before my question, I want to make sure I understand so that my question makes sense. So you created this time varying test statistic. And so you detrend the time series and remove the harmonic oscillations, and then you fit your volatility model to the residuals. And then so you have this volatility time series. And then you have a test statistic. Is that being applied at every single point in that volatility?
That's a good question. In the first part, yes, in the second part also, but in two different ways. So the answer is yes. You do
Okay.
it for each.
So
That's
then,
why.
yeah, so then do you have to worry at all about like multiple hypothesis testing? Because like, I mean, the test statistic is changing with time, so that makes me think maybe not, but at the same time, it is the same underlying test statistic. So have you thought anything about that, or?
We didn't think about that, and the reason why is that, especially for the first part, this is a local approach. So you at a certain time point, so the way you calculate this S of t, yeah, this is a robust estimator. It's a modified version of the mean absolute deviation. We use only values of the time series before t. Yeah, so the structure really changes. So yeah, I guess one could think about multiple hypothesis testing, but the idea is really to do the job locally in time. In
Right,
principle,
okay.
you're doing the job at each t. It's not a global test, it's a global test.
Right, okay,
Yeah.
thanks.
You're welcome. So
I'm
Yeah.
sorry, if it were a global test, then it wouldn't be a problem. I think it's the fact that you're doing many local tests that makes a statistician worry about multiple testing.
yeah, I understand the point, but the idea is that at each time point, the structure is changing.
It
So I'm
doesn't
not
mean
sure-
not multiple tests. Multiple tests just mean you have a certain probability of rejecting a test, one test, even if they're all independent tests. If you have multiple tests, your chance of falsely making false detections grows.
No, I agree. As I said, we did not think about multiple testing. We simply did not think about that, and because we really want to focus on the local structure.
But in the end, I mean, this only influences like the choice of the detection threshold.
Correct.
Right?
Yeah.
And I mean, you can always just simulate, for example, just determine the fault detection ratio from.
I mean, especially when it comes to non-parametric detrending, the goal, that's something maybe that I did not emphasize yet. I mean, DVDs.
Oh, David.
Oh, David. So just to follow up David's question. Yeah. So I should have emphasized that. So when we test for the presence with this local approach of a flare, we do it with the goal of detrending the time series. So here in the first part of the algorithm, we are not detecting flares yet. We want to delete the points in time, the corresponding values of the time series that are corrupting the estimation of the trend. Yeah. So and that's why, strictly speaking, I don't care about multiple testing from the first part of the test. I simply don't care.
Yeah, it's like cleaning the data.
Exactly.
And so, you know, there is C-bar rejection spectrum.
Yeah, but it's a very, both were very good questions, but strictly speaking, I really don't care in the first part whether I have, say, a test or a multiple test, because the goal is to detrend the data, or as said, cleaning, say, the data in the sense that, so removing those observations that are such that I cannot fit the trend, the harmonic trend, the time varying trend properly. Precisely enough so that in the second step, my flare detection is good. So in the second step, what we do, actually, before going into every single step of the algorithm, in the second step, once I have obtain, say, a good fit for the harmonic trend, I remove from the original time series the very last version of the harmonic trend, and I get, say, between quotes, the best version of the residuals. And it is to those residuals that fit the gauge. And once I have a gauge fitted to the residuals, I can work parametrically, as if that time series was a financial time series. Yes.
But that's where exactly the overfitting happens, right?
Say again?
I said,
Yes,
you said you don't care
correct,
about it, but
correct,
that's where the
correct.
overfitting happens. The
In
first
the first
step.
part or the second part?
First part. Well, first part, obviously
Yes,
you're doing
I-
something if the first part helps you to make a selection, right?
That's correct.
And that's where
no,
overfitting, that's
No,
open.
no, sorry, no, maybe that was a misunderstanding. The
Okay.
first part is about, I guess they can see me from the camera.
They
right?
can see you,
Ah,
yes,
okay.
but
They
they
can
can't
close the
see
screen.
what you're.
Yeah, we can hear you.
Okay, so in the first part, which is called non-parametric detrending,
Yeah.
the goal is to obtain a good, say, deterministic fit of the harmonic component. Yeah. And to this end, I do the test local in time. As you said, I'm overfitting, right? But in the end, the goal here is to simply delete those observations that are such that when I fit, say, my harmonic curve, yeah. They can say generate or say produce some bumps that are not there. And if the more corrupt is the harmonic, the less able I am in the second step to do the flare detection. So it is in the second step that we really do the flare detection, not in the first step.
So do you filter?
I understand that. I said detection of second, but I'm, maybe I'm not understanding that well. But whatever you're doing the first step, it's going to affect you, whether it's type 1 error or type 2 error, right? Because there's no free lunch. Otherwise, if the first step truly does not matter, you don't do it. The reason you do it, obviously it matters. So I'm just trying to see, it might be doing a way that actually is to your benefit. I just want to see formally how that affects your conclusion in the end, because obviously it's a data dependent operation. So there's always a worry when you have data dependent operation. So I guess that's probably David and I's, the question will be seeing, it could be beneficial, it could be hurting you, but just like, how do we think of them probabilistically?
It's a very good question, and it makes perfectly sense. Yeah. Of course, I mean the results are gonna be depending on that first part, right?
Yeah.
Yeah. But what I was trying to say then when I go to the second part is that it is more on the second part of the algorithm that I see eventually the need of a multiple testing. Because here we are really saying, okay, if the p-value is smaller than alpha, then I say that that's a flare. Right? And that's where we really do.
Can I so suppose instead of doing this parametric fitting, suppose we have done a wavelet decomposition, shall we, let's say. And then kept only the largest scales or something based on some tests.
That's a good idea.
That is, that is pretty much what is being done here, right? So, I mean, I think getting the baseline that fits that fits, I mean, getting a model for the baseline that fits the data outside of the flares is probably what we want. So, and there's a big mismatch in time scales between the flares and the baseline. So that is probably helping us a bit. Where, in a general sense, maybe if we had a flare that might last a long time, it would actually, this method would not work.
Okay.
But because the flares are all spiky, it's actually, it's not been a problem.
Actually, so I want to mention that since you brought it up, so we tried wavelets, we tried splines, and the results were not as good as this approach with time varying harmonic combined with the flare deleting same.
And there is a reason to use a harmonic here because we believe we know where this harmonic oscillations are coming from. They're from star spots. So there is a periodicity in the star with some range because of differential rotation and phase of the spot and everything. So it's the fact that everything is focused on a narrow range of frequencies is meaningful, physically meaningful. That's probably helping us a bit too.
Renee, do you remind me, is this a very similar situation as like my former students, Alex Blocker worked on, right? We're kind of removing these long-term trends, right? We don't want it too small, too frequent to say we do not want it too low. We want it somewhere in the middle, right? So you do that. Okay.
Actually,
that I
the
complete.
problem that
Yeah.
the problem that
Go
Alex was working on was actually was harder because there was a vast range of scales in the signal that spanned from small to large and through the middle. Whereas here, the signals that we're after are really very, very spiky compared to the. Can you bring up one of your examples? Light curve, and you can see what that looks like.
I mean, in the beginning or
Any of those light curves.
maybe not here, right?
Yeah,
Oh,
yeah.
here actually.
Yeah. Look at that. So the flares stand out very obviously and clearly compared to this one. So I mean, I guess you're right that we should care about this, but it has not been a problem.
So it is not a cosmic ray.
It's not a cosmic ray. No.
Because this looks like,
No.
the spikes are red.
What is a cosmic ray?
No. it's like-
I guess, Vinay, there's one important thing to keep in mind, if I understand this correctly. In the wavelets decomposition, let's say if these noises are Gaussian, right? These wavelets at a different frequencies, the coefficient are independent of each other.
Yes.
Okay, so in which case it's legit for you to choose something because these coefficients are independent of each other. So it's legit to determine the problem by eliminating something according to one set of coefficient and to do analysis on the other set. These two sets are independent. Because independent, all the condition distribution will be still the same. Right? I'm not sure for this criteria here, do we have that feature? Like the way you select those things, the criteria you select those things, are they independent of the way you can analyze the data for the selected part later? If there's dependence, then it's a little bit more trickier.
Yes and no. We were just discussing this earlier. We decided that yes, they need to be independent. They were actually
decided to be independent. I like that.
Yes. Currently, you're right. There is we're using similar thresholds for both the steps. But in principle, the numbers are the values that are used are different. Even though the parameters that are used to do the signs are different, but we happen to be using the same values.
Even when they're even if with different values doesn't necessarily mean they're independent. They still be heavy correlations, right? It's just not these wavelet coefficients you can formally prove they're independent of each other, right?
Yes.
But I don't think the dependence itself is a problem but the question is like if your second stage all your probabilistic statements are conditioned on the first stage, that'd be fine. Right, that'd be fine. I mean, it depends on how you make these statements. If they say conditional on these being selected, or we have these properties, that's fine. It's if you make these unconditional statements, and that could be quite a bit of problem if they turn out to be very, very dependent on the first.
Yeah. That's a good point. Yes.
Yes.
Yes. The second part is definitely conditional on our finding a proper harmonic baseline.
Actually, we were even thinking of, rather than removing one single point corresponding to the flare, like an interval of points, right?
Yeah, that could be that. But
That's also.
but that's just putting Band-Aid on it. Yeah.
Those are very good questions.
One more question.
Yeah.
In the first stage, what is the assumption of the noise? When you
Oh,
remove the
Gaussian.
Okay, just Gaussian.
Yes. But this is also
Actually,
calculated.
no, not even that. I mean, it's just assumed to be homoscedastic Gaussian.
Yeah.
Because it's
Yeah.
just based on, I mean, it's not even using the measurement error, it's just scattered in the light.
But for the second part, for the gauge part, say for this part, there are several different options can be used. Yeah. Very recently, some people are working more with say asymmetric t-student distributions and heavy tails distributions. But for the first part, this is a half normal quantile, so we are assuming that the epsilons are Gaussian.
Oh, sorry, I just noticed that Shauli put in a reference to a paper here.
Okay.
And it goes to something called game theoretic statistics and safe anytime valid inference.
Yeah,
this
I
about?
was. Yeah, I would just lift very quickly. It's may or may not relevant because currently there's a development of these inference procedures. It's another way to think about multiple comparison, particularly with the time component. You try to come up with these procedures, these confidence intervals, for example, they are a little bit wider, but they kind of covers anytime you want to look at something. So it's a more simultaneous way of doing it. The price you pay is a little bit wider. So I'm just wanting to, since we talk about multiple comparison problem, this is the more recent development. There are a bunch of these things called anytime valid safe inference. So I just want to let you know.
Thanks for sharing that. Okay, so
Oh, we are close to an hour, by the way.
okay,
So we should probably, wrap up as,
Yeah.
within a few,
so
5 minutes or so.
yeah, so this is in the very beginning you have your first guess for your trend. You define an alpha max, and then you choose a certain number of iterations. You define your p-value, yeah, and if so, the p-value is smaller than the alpha at the first, starting from the first step till the I step, then you delete the pair. Otherwise, you simply define YT at the next step as the previous one. And this is outside the loop for T, so it depends only on I define the updated versus say the updated residuals as so the data minus the fit. And here you have also the updated alpha. Yeah, it is given by the maximum of those alpha over T such that the p-value is smaller than alpha at the step I. Yeah, so you are picking the largest among all the p smaller than the alpha that you had in the previous step. And this value of alpha is guaranteed. So alpha is guaranteed to decrease over I because the inequality appearing in both the conditions is strict. Huh? So this inequality and this inequality. Okay. So at the very end, when you're happy with your trend, then you fit a gauge. And then you apply the parametric test. And this notation here, I added this notation to mean that, so you want, of course, the p-value to be smaller than alpha to say that's a player. But also, and this is the difference between the second part and the first part, yeah, you are only looking at positive values, say of X, whereas in the first part, you are also removing or deleting from so your data set, those values of X that are also, say, very negatively large. Yeah. You want to remove values of X that are, say, very negative because those values are also affecting the quality of your estimated trend. In the first part, I really look at absolute values. In the second part, I want only values of X that are very large. So so if the product of these two indicator functions is 1, then I finally define that time point as such, the corresponding Y is a. So this is the algorithm. And now I want to show you, since I only have how much, 15 minutes or 10 minutes?
5 minutes, 5 to 10 minutes, let's say.
Okay, so I'll show you how this works. So present this. So among those time series, I So I picked the most difficult one. So this is so the first part of this time series in particular, you see you have time varying amplitude, time varying frequency. So this is the time series. It has a very special structure, changing over time. Say both the deterministic part and the random part. Some very evident flares, some less evident ones, like this one maybe, right? This one, or maybe this one. So this is the harmonic fit, yeah. And you get the residuals. Then this is, so you compute the p-values, and so this is the p-value that you obtain, say, at the last iteration. So you see you are basically removed, you have removed almost all the points that you were not willing to use when fitting the harmonics. And these are what we call extreme values. As we said, these are values that we do not call flares, yeah, because we are still in the first step. Remember, we are doing this job to get the good trend mu. So we call them extreme values rather than flares. So for this specific time series, using AIC and BIC, we fit the Garch 3-1. So this is the conditional variance. Yes, and then then you subtract to the original time series, say the last fit, and you obtain the residuals. So these are really the residuals to which you want to fit the Garch. Yeah, and here I just wanted to show you that basically if you use the non-parametric bound, yeah, you tend to estimate many flares, yeah. Whereas instead we use the parametric bound because we want to use the structure that we have in mind for our residuals. Yes, and so these are, again, so if you look at the conditional variance, yeah, some of these points in the volatility correspond to very large negative values. Okay, and so finally, this is the final result. So we only look at those extreme values that are positive. So this is the final result for this specific chunk of, say, what we had in mind as being the most complicated time series. And then here I have a summary for all the others, just in one figure. So this was the S4. So this is actually the same status as the one I was studying here. Yeah, but a different chunk, different.
Let me ask you a question on the previous figure. So I'm very much not in the astrophysics space, so feel free to call this a very stupid question. But at time point 2152, roughly there, to me that doesn't look much like a flare.
Sorry, which one?
This one.
Yeah, that one.
Ah,
That looks like it's pretty smack dab.
Yeah.
Like the estimated trend.
Yeah, I don't know. Johnny is online. Johnny, are you there? So Johnny is the student who completely implemented this algorithm.
yeah, John is there.
Yes.
Yeah.
So your name again?
Here.
Peter.
Yes.
Yeah. So Peter was pointing out this specific detected flare, right? Is that correct?
Yeah.
Can you see that, Johnny?
Yeah.
So
So I think it's not like visually significant because you see there's a decreasing trend. See, but if you do the after you detrain this harmonic base, then you see if you see that on the residual
actually I can go back to the previous plot. Yes, so if I maybe point here and I go up, this corresponds to this residual.
I know it's the one further left, but I see what you mean.
So again,
It's a bit further left.
it's not this one.
It's this one. 2152.
Oh, it was another one. Okay.
This one, right?
Yeah,
It's obviously marginal.
Okay.
Yeah,
Oh,
yeah.
they're not on the same scale then. Oh, they are. Oh, here, this one.
Yeah, it must be some
So yeah, that was just really
tiny
fun, but-
little, right.
So,
I'm not an astronomer either, so.
but that's interesting threshold, right? Because you may I mean, this may not be a. flare.
Yeah, I mean, this at 0.9, right?
Yeah.
I mean, in any catalog that you produce, you want to provide a measure of significance.
Yeah.
And, yeah, I mean. that's
Yeah, you push
probably-
that and it'll be top and
It'll go away, yeah.
So my question was about the points where we try consistently on the flare, like when we go back to the flare,
Yeah.
with red points. 2154, like here.
Yeah.
The large,
these ones,
no, the next one over.
this one.
You have several points. there.
Oh, yeah, it's
So-
actually not one spike. I mean, the spike is.
Yeah, there are several spikes,
Yeah.
but
No. I mean, it's actually resolvable if you zoom
yeah,
in.
I know, but in this algorithm, do you determine this as one flare or as continuous of 1, 2, 3, 4 flares?
That's a good question, huh? It is really due to the fact that, yeah, when you go back
Yeah.
here, you see, this is
Yeah.
the chunk of values.
Yeah,
Right.
Yeah,
But-
that's why I was more into having some local neighborhood for the flare. And detecting a flare, if, for example, before the spike, a little bit before the spike, there is a drop as well. These are, so for example, this is what I had in mind, if you remember also after discussing with oops.
But even, even from the physics, it is important to know whether there is a secondary, you can have the trend going up and then you can have some
yeah, I mean.
flares on that trend. right?
So I should mention that, this is still step one of the full process.
Yeah.
Once we know where there's a flare, what we need to do is some sort of fit the profile and get
Yeah.
the flux. So
But
if
you
there are,
fit the all four
Yeah,
points
mean,
as a one or as a four?
as a variable, as one,
Okay.
right? I mean,
Yeah.
if there are adjacent points, they're gonna get mashed up. They're mashed together into one single.
But one possible answer to Anita's question is here, so if you think that there is no change in the variance, then this is zero, and basically you end up with the standard process.
Mhm.
But then you can think of some, say, variations that are proportional, say, to the change, to the deviation from the baseline. And you have here an indicator function and say, okay, you are exceeding the threshold, and at the same time, before that specific point in time, say t minus delta, you are going below a certain threshold. Because it happens often that right before the peak, it's a fall.
Yeah.
So that's something where, right? But perhaps it looks just very too much complicated for the goal of this specific paper. Yeah.
But it's interesting because, this, the way to characterize the flare is not trivial.
No.
Having an algorithm which determines the possible locations for the flares and then going, as soon as it's to the next step is interesting. and important.
When I ask Vina what is play, he just point them out and down.
Yeah. because that's something-
There is no dispute about what the big flares are. The difficulty is when you go to the smaller.
So we can train neural net on.
Exactly. Yes. I mean, human lens, right? I am trained to recognize big flares.
Yeah, because you're thinking about sound as the
Mm.
possible kind of time out there
Sure.
closer eye and then move this far away. And, it's different. Right? Yeah, you can see. on-
This is one way to do the test. You can also look at the p-value. I'm not sure I have that figure here. Yeah, so these now the blue ones are p-values, and value p-values, and the red one is alpha. Okay, so I guess that's it.
Thank you. Okay, it's obviously, work in progress. We haven't finished the thing yet. So any comments that you all have, it's absolutely useful. So questions,
I was wondering about so the flares were seeing statistically obvious which one are flares, and maybe you to me, but how would use flares, like how important is to actually observe all of them instead that do you need to be conservative and potentially like set a lower threshold that maybe you would have, and so you end up like selecting like the points that are like slight flares or maybe not flares, just because you want to be sure to actually capture all of the flares. And so,
I think he has something.
No, I was just wondering, so you had the overleaf up, can you bring up the?
Overleaf?
Yeah,
Yeah.
there was this figure with the injection power calculation figure.
Yeah,
So you can-
we have a partial answer to your question.
Yeah, exactly. That one.
Yeah.
Ignore the me, but the figure is legit, and it's showing the difference between the parametric versus the non-parametric flare detection process, and the oh no, that's okay. And what's being done is we're injecting flares at different intensities according to what's on the x-axis, and checking to see how many times they get detected again. So the parametric clearly is doing better than the non-parametric at the low flare end. Well, I think this is the y-axis is in percentage, but it's actually 20 flares indicators or something like that. So 19 or 20 times it was detected all the way down to a rate of 1/10 of the maximum. So it's at least we are sure that this working down to the 10% level at that flux completeness. Below that is still up in the air.
How are you determining the like cutoff for what is where and what's not? Like on the previous, you had shown a plot that had like the red dotted line at 0.9.
Yeah, actually, this
Are
is
you-
also
The
adaptive.
alpha?
Yeah.
Oh,
It's
it's
also-
completely up in the air.
Okay, because like it could be interesting if you have some sort of like optimization where you assign like a penalty for a error detection and then like a reward for a correct detection and try to
Yeah.
optimize the alpha based on that, based on your.
But actually, the alpha is also kind of optimal here.
It's
comes out-
optimized?
It comes out of the alpha.
Oh, right, from the couch. Oh, yeah. Right.
Comes out of the alpha. Yeah. So you see, you fix this alpha max, and then at each step you say, okay, my next alpha is gonna be the largest pi among the pi that are smaller than the previous alpha. So basically, you start with an alpha max and you decrease, up to a point where basically you are not.
But that is the detrending. I'm sorry, that is the,
Oh, the second alpha is another alpha.
yeah,
This alpha is another alpha.
yeah. I mean, I think that's the one that.
Yeah, it's like. the
You're referring to the parametric part.
Yeah,
Oh, that's another alpha, yeah. And that's something that you fix.
but
Okay.
yeah, I mean, you could put some penalty.
Yeah, like I was just wondering like how you're optimizing that value and the idea of like having a penalty for,
I mean-
like varying alpha and having a penalty for incorrect ones. And versus like a reward for correct ones and optimize what lines like shows that line. That's super interesting.
I mean, when we made that power plot, what I was expecting to see was that the parametric one would also plunge along with the non-parametric, just didn't, so we need to, explore that in the. Okay, any other questions? If not, it is now 1:30, right on time, Giovanni. So let's thank Giovanni again.
Thank you.
Thank you for being there. Thanks for your
Okay.
time.
Okay.
Let me turn off the recording, stop recording.